I came back yesterday by plane, so I prepared the lecture in the plane, and I slept very few hours. So if anything seems fishy, please tell me. I will try to correct myself. Okay, so let me try to recall what we saw on last lecture. So we introduced the notion of increasing events. And the idea was that an event is increasing if adding edges to a configuration only makes it more likely to be in the event. Okay? And what we saw is that increasing events are positively correlated. So this was FKG inequality, FKG Harris inequality. So what we saw was that so we proved it only for A and B that depends on finitely many edges. But in fact, by approximation, it's valid for any increasing events. And OK, maybe when we applied it actually for events that depend on infinitely many edges. But for these events, our proof is somehow sufficient because we know how to approximate them. So if you remember the application we had for Harris inequality was Zhang's argument for to prove theta 1/2 equal to 0. So the idea was to say, if I consider the box lambda n, so lambda n is, this was n to 2, minus n to the 2. On lambda n, okay, we showed that with probability going to 1, we should have a path from the north. Okay, or from any given side, the probability of having a path starting from the side going to infinity was going to 1. Okay, and this was using FKG inequality in a subtle way, using what's called the square root trick. Okay, so from this we could deduce that, okay, with a large probability, we had two open paths, and using the same argument for the dual. Okay, we saw that we could construct also paths from the west and the east side, but in the dual graph. Okay, and then closing all the edges inside the box, we obtained a contradiction to the uniqueness of the infinite component. Okay, so the idea was to suppose that theta is positive, to say that, okay, if theta is positive, with probability tending to 1, I have a probability linking the box to infinity. Using the square root trick, so using FKG inequality, with large probability, we had a path going from north to infinity and a path going from south to infinity. And then using the same argument for the dual, the fact that the percolation is self-dual, we could construct something in the dual to separate these two paths. Okay, so this was also the first step to our quest in proving that PC is equal to 1/2 for percolation on Z2. Okay, so now what is the next step? So we want to prove that, so this is called exponential decay of connection in the subcritical regime. Okay, so what we want to prove is that if P is smaller than PC, so then there exists CP positive such that the probability that 0 is connected to the boundary of the box is equal to exponential, is smaller than exponential minus CPN. Okay, where here this thing is just lambda n minus lambda n minus 1. Okay, so this is the set of vertices of lambda n that are adjacent to the complement of lambda n. Okay, so so this is actually valid in ZD. This is quite general. Why is it interesting in Z2? So if you remember, we had seen last time that I think we had seen exactly this. So then we see that 1/2 is smaller than, sorry. Yes, is, yes, larger than PC of C2. Okay, we know that when P is strictly smaller than PC, the probability of having a connection of length n is exponentially small in n. Now this makes sense. Therefore, we have seen last time, and I will come back to this argument actually to prove something better. We had seen last time that at 1/2, the probability of being connected to the boundary of the box was larger than 1/n, okay, up to a constant. So therefore, it means that 1/2 cannot be smaller than PC, so therefore it's larger or equal to PC. Okay, and well, because this, okay. We have already proved that PC of Z2 is larger than 1/2. Okay, remember that PC of ZD is the infimum of P such that P, theta P, is larger than 0. Okay, and it's a regime where we have a unique infinite connected component. So therefore, these two arguments combined, they give you that PC of Z2 is equal to 0. Okay, and I should put the two always at the same place here. Okay, so I think we are going to prove this next time. Maybe we will finish the proof on Friday. What we are going to do today is to, well, introduce some prerequisites for this proof. So there are two of them. So the first thing is the BK inequality, meaning the Vandenberg-Kesten inequality. And the second thing is Rousseau's formula. Okay, so well, this BK inequality, it's something, well, in the same flavor as Harris inequality, but it looks at something, a different operation on events. So it says that basically, if you compose two increasing events in a certain way, then you have an inequality which is the reverse of this. Okay, and I'm going to introduce what's this way in a moment. And Rousseau's formula, it's a simple formula that gives you an expression for the derivative with respect to P of the probability of an increasing event. Okay, so any questions so far? Okay, so let me define the notion of, well, kind of, well, the operation on events that we want to consider for BK inequality. So for A and B increasing events, we want to define the event A circle B to be the event that spells like this. So A and B are disjointly satisfied. Okay, so I will just give a definition for this in a moment, but let me give you an example to try to motivate this definition. So okay, so let's assume that A is equal to the event X connected to Y, and B is the event X prime is connected to Y prime. Okay, basically we want to say that the event, this event should be the event X is connected to Y, and X prime is connected to Y prime using disjoint paths. Okay, and more precisely, I want to say that they are using edge disjoint path. Okay, so basically, this event here will be satisfied if I can find a path like this and a path like this, okay? Which are not using the same edge, okay, and which are open. Okay, so this, okay, this works. this would work as well, okay? But for instance, yes, if I have a configuration where, I don't know, I have just x, y, x prime, y prime, and I have only closed edges around, well, here, A circle B is not satisfied, okay, because I cannot find two disjoint paths, one which is linking x prime to y prime and x to y. Okay, because if I take an open path from x to y, okay, then I can't use this edge to link x prime to y prime, and I'm kind of stuck. Okay, so basically, this is the intuition for the definition, and now I want to find a way to generalize it to general increasing events, okay? Because it's kind of clear what it means from connection events, okay? But this thing of being disjointly satisfied, okay, I have to find a way to make this definition work. Okay, to find a formulation basically for this definition for general increasing events. Okay, so if A is an increasing, so I will just introduce a definition in order to make possible this definition here. So if A is an increasing event, and I is a subset of E, we say that I satisfies A if all the edges in I are open, then A is satisfied. Okay, so an example is, well, if A is the event, X is linked to Y, and I is a set of edges that contains a path linking X to Y, then I satisfies A. Okay, so mark. So if omega belongs to A, then there exists I in E such that I satisfies A and I is open for omega. Okay, so why is it so? Has anybody an idea of why this should be true? What I can we take? So, okay, one solution. Well, I guess it's the only solution in this generality. We just take I to be the set of E that such that omega E is equal to 1. Okay, the set of open edges for omega. Okay? And then what we have is that if omega prime is such that omega prime E is equal to 1 for all E in I. Okay, I call this IA. Sorry. This is I omega. Okay, then by definition, omega prime is larger than omega. Okay? And by definition of an increasing event, then this means that omega prime belongs to A. Okay, so now I can, when I have introduced this notion, I will be able to define this event. So basically, we say that A and B are disjointly satisfied if we can find two disjoint set of edges, one that satisfies A, the other that satisfies B, and both set of edges are open. Okay, so exist I1, I2 included in E, I1, I2 disjoint, I1 satisfies A, I2 satisfies B, and omega E is equal to 1 for all E in, okay, maybe I should put the quantificator before, for all E in I1 union I2, omega E is equal to 1. Okay, so in words, A and B are disjointly satisfied if we can find two disjoint set of open edges that satisfy A and B respectively. Okay, so this definition really corresponds to what I drew here in the case of connection events. Okay, two remarks. Maybe the second remark can be left as an exercise. So the first thing is that that's the opposite. A circle B, it's always included in the intersection of A and B. Okay, and the reason why it is so, it is just this observation here. Okay, basically, what you have is that you take away this disjoint assumption, what you get is just the intersection. Okay, so what you have here is a more restrictive event. Okay, and the second thing that you can check is that A circle B is increasing. Okay. Well, intuitively, it's kind of obvious. If you open more edges, this is more likely to be true. But maybe you can try to check it in more details too. And okay, what is BK inequality? Well, it tells you that if you don't look now at the intersection, but if you look at now this disjoint satisfaction of events, then you have the reverse of FKG-Harris inequality. Okay, so. Theorem. So if A and B are increasing and depend on finitely many edges. And this time it's important because the way to take the limit with this kind of operation on events is not obvious. So we will restrict ourselves to apply it in event that depends really on finitely many edges. What we have is that the probability of A and B being disjointly satisfied is smaller than the product of the probability. Okay, so I will give you a proof of this, but before, what I want to do is to give you a first application of this inequality. And the idea is to improve the bound we had on the lower bound we had on the connection probability at p equal 1/2 for Z2. So, proposition on Z2, what we have is that P 1/2 of 0 connected to, well, this is larger than 1/2 square root of n. Okay, so okay, what's the connection with the FKG inequality? Well, let's remember how the kind of thing we consider to prove a lower bound on this in the first place. So what we were considering is gamma n, which was, I think, something like minus n times 0 to n minus 1. So just so this is for n equal 2. Okay, so the length here is 2n, let's see. No. Yes. Okay, the length here is 2n, and the length here is 2n minus 1. Okay, and you can see that when we're trying to cross this rectangle, we are using edges in this graph, okay, because we don't need the edges there. And this graph has the property of being self-dual, okay, in the sense that it's really well, its dual is just itself, but rotated by 90 degrees. Okay, so what we saw last time is that because of this self-dual property, well, the probability of having a crossing from left to right in gamma n was exactly 1/2. Okay, because the idea is that either you have a crossing from left to right in gamma n, or you have a crossing from top to bottom in the dual. And because the two graphs are isomorphic, this probability must be the same. And because the sum of these two probabilities is equal to 1, then each probability has to be equal to 1/2. So this is gamma n, and this is a left to right crossing. So when I'm saying left to right crossing, I'm saying that there is a path that is starting from the left side and that is going to the right side. But this path, I can take it self-avoiding just by erasing the loops when I construct it. Okay, if I have a path which is not self-avoiding, which is joining left to right, what I can do is follow this path, and each time this path forms a loop, I just erase it. Okay, in the end, I will get a self-avoiding path. Okay. So now this, okay, so this event, I can rewrite it in the following manner. It's equal to, well, the probability that there exists x0 in 0 to n minus 1 such that there exists a self-avoiding crossing from, okay. Okay, let's see. From left to right. Going through x0. Okay, this is, okay, what I'm saying is just, okay, here it's, remember, on the abscissa, 0 is the middle point, what I'm saying is that this path must go somewhere in the middle, okay? So I'm just saying, well, the event that there exists a crossing from left to right, it's the same thing as saying that there exists a crossing from left to right and that it uses some point in the middle, okay, in this middle segment. And of course, okay, my drawing is not, but this point is not necessarily unique, okay, but okay, no, this is not x0. Okay, let me call it x. So, okay, so now this thing, it is smaller than the sum over x of the probability of, okay, exactly this. 0x okay, I've just rewritten this event here, but without the quantificator. Okay, I'm just saying, well, this is a union over x, so I can use a union bound. And now what I have is that there exists x0 such that the probability of okay, well, this thing is almost square, in fact, but 0, 0. Okay, maybe blue is not. Is blue easy to distinguish from white or not? Okay, so maybe red is better. I don't know. Everything looks white on this board. Okay, and this is larger than 1 over 4n, okay? This is from x equals 0 to 2n minus 1. I have a sum with 2n terms. I know that this sum is larger than 1/2, so one of the terms has to be larger than 1 over 4n. Okay, and now is the important bit. So this event here, okay, when this event is satisfied, you can see that from 0, x0, I have two paths that are going at a distance which is larger or equal to n from 0, x0. Okay? Because they are ending at a distance which is, well, larger than n. Okay, in the sense of the infinite norm. Okay, so this thing, it is included in the event z 0 x0 Okay, so this is the event that 0x0 is linked to the boundary of a box of size n, but which is centered on himself. Okay, and well, this event is in fact satisfied twice disjointly. Okay, in my definition, there I never say that A should be different. A and B should be different. Okay, so what I have, so let me call this x bar 0, maybe. So what I have is that P1/2 x bar 0 connected to x bar 0. This thing, okay. This is larger than 1 over 4n. Okay, and now I know that this is smaller than the probability of the event square, just by BK. Okay, so by BK, I get that the probability that x0 is connected to x0 plus n is larger than 1 over 2 square root of n. Okay. Here by translation invariance, okay, we can just shift everything back to the origin. Okay, we get the same now. Okay, so we get something but with a power which is well, just half of what we had before. And it turned out that it's actually conjectured. Okay, we will see an upper bound on this, that this decays at least like some power which will not be really explicit. And it turns out that, well, the conjecture is here that this decays like some power, and this power is a fractional number. I can't remember exactly what it is, but these exponents can be predicted using well, conformal invariance. Okay, this is something we might get a little bit into when we look at when we come back to the self-avoiding work. Okay, so is this proof clear? Okay, so now let us prove BK inequality. Here. Okay, so we say that the events depends on finitely many edges. So basically, I can reduce myself to the case where E is just a finite set. And then I will just use the notation omega I for omega EI, okay, just to simplify the writing. Okay. So here, the main idea for the proof is interpolation. So basically, we want to construct a sequence of events, the first of which whose probability will be this, the last of which will have this probability, and we want to check that this sequence, the probability of these events is a decreasing sequence. Okay, so the idea is to modify things little by little and check that we have inequality in each step so that in the end you get this inequality. So what we are going to do is to duplicate the edges. So now we are considering not one event, one environment omega, but we are considering two of them. So omega, omega prime, it will be an element of 0, 1, to the e square. No, sorry, to the, yes, no. Yes. So this will be basically 0, 1 to the 2k. Okay, so basically for each edge, I'm going to consider two variables, omega e and omega prime e. Okay? And I will use the same notation, but now this is, okay. Measure on 0, 1 to the 2k. So basically, under PP, omega and omega primes are two independent copies of the environment. Okay, so. And now I'm going to define omega hat. Okay, so for n in 0k, what I'm going to define is omega hat n, which is just the event omega 1, omega n, omega prime n plus 1, omega prime k. Okay, so I'm defining an event, an environment omega hat, which is just, well, for the edges numbered from 0 to n, I'm looking at omega, and for those numbered from n plus 1 to k, I'm looking at omega prime. Okay, and well, now with a bit of abuse of notation, okay, I will define. Okay, so. No, A and B are events in omega. Okay, now we have a larger space omega bar. Okay, but I will just say that basically omega prime belongs to A if omega belongs to A. Okay, so to satisfy A, I will just look at the edges in, I will just look at omega. For B, it's a bit different. What I will define is an event Bn, which is the event omega n belongs to B. So I'm trying to satisfy B, but now the variables I'm using are exactly these ones. Okay, and if you look at this now, what you have is that bk is just b, if you want, and b0 is just the event that omega prime belongs to b. It's just b, but I'm looking at the environment omega prime instead of omega. So what we have in particular, okay, is that well, pp of a intersection, okay, sorry, a circle b0 is equal to pp a pp b. Okay, so if I'm trying to satisfy disjointly a and b hat 0, well, in fact, I mean, I know that to satisfy a, I can only use variables omega, okay? And to satisfy b0, I can only use variables omega prime, okay? So if you want, here I can only use the first set of edges, and here I can only use the second set of edges, so these things will naturally be disjoint. Okay, so it's exactly the probability of the intersection, and because they are relying on disjoint edges, these things are independent. Okay, on the other hand, what I have is that, well, this is, well, simply the probability that A and B are disjointly satisfied. Okay, if you want, the difference is that here I'm looking at things at a bigger space, but anyway, the variables omega prime here don't play any role because I don't look at them to know that if A and B are satisfied. Okay, so what I've been doing here, I've duplicated the edges, and at the beginning I'm allowing B to all these duplicated edges, and step by step I remove one of them. Okay, and what we are going to prove is that for all n in 1k, we have pp a bn is smaller than pp a b n minus 1. Okay, so if this is true for every n, basically, what I have in particular is that I have that pp a b k is smaller than pp a b0, which, according to the above remark, is exactly what we want to prove. Okay, so what we are going to show, in fact, is that this inequality is true if we condition to the state of all the edges that don't have index n. So both the edges and the prime edges. Okay, so we prove star after conditioning with respect to omega I, omega prime I in 1k minus n. Okay, so basically, I mean, we have 2 to the power 2k minus 2 possibilities for this, okay? And for each of these possibilities, I'm going to show that if I'm conditioning to the value of this variable, this is true. Okay, and then you just have to multiply the probabilities, and you will get the inequality for this thing. Okay, so I will call Pn this condition probability. Maybe I will not raise this. Okay, so basically I have 3 possibilities. 2 of them are trivial. So first possibility, okay. If this probability is equal to 0, then star is true. Okay, so what does that mean that this probability is equal to 0? This is that, okay, I erased my definition. This is quite bad, but it is that A okay, so this means that this event is not satisfied even if when I open these 2 edges. In fact, if you remember the definition, these things don't care about omega prime. Okay, so it's not satisfied when omega n is open. Okay, when the nth edge is open. Okay, so in that case, there is nothing to prove. Okay, and okay, here it's actually possible that that this thing is positive. Okay, maybe if the 2 edges are open, there is one way to satisfy this. But so this is where you get that the equality is not easy. Okay, so you will see. I mean, this happened in the 3 cases, but this is why the inequality is not an equality. In general, it's strict unless you take events that depend on distinct collection of edges. Okay. The second thing is that, okay, what happens if P n A B n minus 1 is equal to 1. Okay, so this means that A Pn minus 1 is satisfied even when omega n is equal to omega n prime is equal to 0. So even when both edges are closed, this thing is satisfied. Well, in that case, it's not difficult to show that okay, it's necessarily smaller, but in fact, this is also equal to 1. Okay, because if you have, okay, basically this means that in this collection of values, okay, basically here you can find I1 and I2 both in the set, both in, well, neither of them includes n. Okay, and if they work for one event, they will work for the other. Okay, but anyway, it's not really important. In these two cases, there is nothing to prove. So now, the last case is if the probability of A Bn is equal to P. Okay, if okay, so if the probability is not 0 or 1, then it has to be equal to P because this event, it only depends on omega n. It does not depend on omega n prime. Okay, and because it's increasing, the event has to be satisfied when omega n is equal to 1 and not satisfied when omega n is equal to 0. And here, what I say is that in that case, then I have two possible values for A Bn minus 1. Well, it's either P or 1 minus P squared. Okay, and this is larger than P. Okay, because P is 1, well, P is exactly this without the square. Okay, so if you're taking the square, you're subtracting something smaller. And to see this, you have to come back to this definition. Okay, so when this event is, if this event is satisfied when omega n is open, okay, this means that I can find I1 and I2 such that every every index in I1 corresponds to an open edge in omega, and every edge in I2 corresponds to an open edge in omega at n. okay? So, because this is equal to P, what this implies is that N has to be either in I1 or I2. Okay, it has to be in the union. So if N is necessarily in I1, so meaning that omega N is used to satisfy A, then this guy is satisfied only if and only if omega n is equal to 1. Okay, and thus okay, so what do I mean by n necessarily is in I1? Here, when I'm saying this, I'm not saying that I1 and I2 are unique. Okay, but it's possible that for every choices of I1 and I2, n is always in I1. Okay, so it's always A that uses this edge. The second possibility is exactly the same thing, but where it's necessarily B at n that uses the edge n. Okay, and in that case, well, you can satisfy this event using exactly the same I1 and I2, but because you need the edge with index n for this event, this is this one that you should open. Okay, but this also has probability P. Okay, and the third possibility is that actually amongst all the choices of I1, I2, there is one for which n is in I1 and another one for which n is in I2. In this case, okay, so n is, okay, can be in both. And in this case, this event is satisfied if either omega n or omega prime n is open. Okay? Okay, in which case I have that Ppn is equal Bn minus 1. This is equal to 1 minus P squared. Okay, it's the probability that I have at least one open edge. Okay, so you see that I have basically two cases where the inequality may not be sharp, okay, which is this one and this one over there, which explains why this inequality is in general not sharp. Okay, so, I mean, the proof relies on a very clever trick, but well, the idea you can take out from it is this idea of basically this idea of interpolation, of doing things one edge at a time. Okay, when you have to prove a big inequality, well, this is something. Okay, this is something quite general that okay has some other application. Okay, so this was BK inequality. And now the last thing we are going to see today is Rousseau's formula. And what we are going to do tomorrow is combine the two in order to prove this exponential decay of connection probability in the whole subcritical regime. Any question on the proof? Okay, so, I mean, basically, I tried to detail it as much as I could, but well, what's important is to remember, okay, this duplication argument, then the definition of this b hat n, and then for this, okay, induction, well, in this step between n and n-1, you can try and okay, redo the details by yourself if you are not convinced by what I did. Okay, so okay, so I'm now going to introduce another definition, which is the notion of pivotal edge for an increasing event. Okay, so basically an edge is said to be pivotal for an event if it's of crucial importance in the sense that if it's closed, the event is not satisfied, and if it's open, then it's satisfied. Okay, and we are going to consider increasing events. So, given E an edge and omega a configuration, I'm going to define the configuration omega E plus and omega E minus as follows. So omega E prime E plus if E prime is in, okay, so for all edges that are not E, the configuration is just given by omega. And what I will have is that omega E plus E is equal to 1, and omega E minus E is equal to 0. Okay, so omega E plus is just omega where I've opened the edge E, and omega E minus is just omega where I have closed the edge E. Okay? So in particular, one of the two things coincide with omega. okay? But if I don't tell you what omega is, you can't tell me which. Okay. Okay, so now we say that the edge E is pivotal for omega and A. Okay. Okay, in the definition I have A increasing and omega in omega, which are fixed. If omega E minus does not belong to A and omega E plus belongs to A. Okay, so an edge E is pivotal basically if given everything that I have outside E, A is satisfied if E is open and not satisfied if E is closed. Okay, so if you want an example, so A is equal to 0 linked to infinity, okay, and E is equal to xy, okay. So the event E is pivotal for A. It is just saying that, well, either two things occurs. So first thing, 0 is connected to x, y is connected to infinity, and 0 is not connected to infinity in omega, okay, minus E. Okay, what I'm saying here is just a set of open edges minus the edge E. Or 0 is connected to y, x is connected to infinity, and 0 is not connected to infinity if I am not allowed to use the edge E. Okay, or another way to describe this event is to say, well, if I force the edge E to be open, okay, if I don't look at omega to know, then 0 is connected to infinity, and all these paths going from 0 to infinity, they have to use this edge E. Okay, so now I will define NA of omega, which is the number of pivotal edges for A. Okay, so it's a random variable. It's really something which is determined by a configuration omega. And what Rousseau's formula says if A depends on finitely many edges, then the derivative with respect to P of PP of A, it's equal to the expectation of NA. Okay, so well, okay, so I've only defined this for increasing event, so I assume here implicitly that A is increasing. Okay, so well, the fact that PP of A is non-decreasing, this is not surprising. This would come for free from the coupling argument we had. If you remember when we proved that theta P was increasing, okay, this in P with the coupling argument, this argument kind of generalized to say that, well, the probability of any increasing event is non-decreasing in P. But now we have an expression for the derivative. Okay, so I will give a proof of this, and we will stop there. So the proof relies on this coupling argument, but okay, basically, okay, so what I could do is just to use the coupling argument as it was before and try to see what's the difference of the epsilon, make epsilon tend to 0, and this would actually work. But, well, somehow if you do this, you have to do it separately for P plus epsilon and P minus epsilon. So, yeah, okay, it's a bit more elegant if instead of considering a fixed P for all the edges, you consider a different P for each edge. Okay, this will make the proof basically cleaner. So, okay, so I replace E by just the set 1K, okay? And now I'm defining P, okay, which is a probability, okay, so P, it's equal to P1 Pk under Pp. What I have is that omega I are independent Bernoulli, each with parameter Pi. Okay, so I'm just defining a measure where, okay, my variables are still independent, but the probability of being open is not the same for every edge. Okay, so now what I have is that dP of PP of A, well, it's equal to the sum from I equal 1 to K of dPi P of A at P equals P. Okay, so I just have to compute this derivative here. I can just take the derivative along one coordinate at each time. Okay. So basically, we need to prove that the pi of p a is equal to the probability that EI is pivotal for A. Okay, because if I do this, then, well, this will be just the sum of the probability that EI is pivotal over I, and this is just the expectation of the number of pivotal edges. Okay. So okay, so now what we can do is just prove that this is true when we condition to the state of all the other edges, and then conclude. Okay, so okay, so I mean, basically, if I look at this, if I'm conditioning to all the rest, basically, you have two choices. So either EI is pivotal, in which case A will be satisfied when. Okay, so if EI is pivotal, let me write this cleanly. So what we have is that P of A, well, it's equal to the sum over omega in 0, 1 to the E minus EI me call it omega bar. Then I get P. Okay, so okay, so I'm not very good at writing right now, but the idea is that you have, you have basically three kinds of, so this thing, it's a polynomial in all the PIs, okay, because it's the sum of over all configurations that satisfy A of the products of PIs and 1 minus PIs. Okay. The idea is that you have three types of configuration. If you don't look at the state of the edge I, you have three types of configuration. So you have the types of configuration where A will be satisfied either if EI is open or closed. Okay, so this is what you have here. And this will give you a polynomial, but that does not include PI. Okay, then you have the configurations such that A is not even satisfied if EI is open. Okay, these configurations, they just won't count. And then you have the configuration that counts only if EI is open. So basically, you will get PI times, well, the sum over omega such that omega 1 in A and omega 0 not in A. Okay, but this thing, it's exactly saying that E is pivotal for A. Okay, so this thing is exactly equal to PI times the probability that EI is pivotal for A. Okay, so it's linear. So when you take the derivative, you get the expression. Okay. I forgot about the first term. So this is this plus PP that EI is not pivotal. Okay, but the important thing is that, yes, okay, so this is always true. Okay, maybe this was the best way to write the proof. So PP of A, it's equal to PP of A in E is pivotal for A. Plus PP of A E is not pivotal for A. Okay, so let me call this A1 and A2. So the thing is that yes, so this event is exactly the event that E is open and E is pivotal for A. Okay, and E is pivotal for A is an event that is independent of EI. Okay, so what you have is that A1 is equal to E is open and E is pivotal. Okay, and these two things are independent. Okay, this depends only on omega I. This is independent of omega I. Okay, so PP of A1 is equal to PI times the probability that E is pivotal. Okay, and PI does not enter here. Okay. And the second remark is that E2 is independent of omega I. Okay, because if I fix the configuration outside of EI, basically, and if I know that this is satisfied, because E is not pivotal for A, I know that it's satisfied even when omega I is equal to 0. Okay, so then it satisfies in both cases, meaning that A2 is independent. So in particular, it's a polynomial where PI does not appear. Okay, so P of A2 does not depend on PI. Okay, so this is where I get this expression. Okay, and when you take the derivative with respect to PI, you get what we want. Okay. So, yeah, if you want as an exercise, okay. Prove Rousseau's formula using the coupling omega PE is equal to indicator that UE is smaller than P. Okay, so basically the idea, if you want to avoid using this okay, P with different coordinates, well, you can just take the difference between P of A and P plus epsilon A. Then what you have to evaluate first is if epsilon is very small, then the probability that omega EP and omega EP plus epsilon differ, it will be okay, the probability that omega EP and omega EP plus epsilon differ in two places, it will be of order epsilon square, so it will not count in the derivative. Okay, so then you can restrict to, basically configuration of this where you have only one discrepancy between the two things. Okay, and these discrepancies, this will contribute to the derivative only if E is a pivotal edge. Okay, so basically this works as well. What's nice here is that, well, you get that the probabilities are affine functions, so the derivatives are quite easy to compute. Okay, so I'll stop here for what we are going to see tomorrow. I don't know of, okay, maybe in the lecture notes of Grimetz, it's now written, but the reference I will use for tomorrow is a paper of Duminil-Copin and Tassion, which is called, a new proof for exponential decay of percolation, or something like that. It's a very short paper, and you will see that, it's, so just to say that what we are going to see next time is not in any of the notes. And okay, maybe next time I will come with the exact reference for the paper.